Hey everyone, welcome to part one of the Meteorology Lecture. So, just as a quick recap, there are four branches of Earth science. There's meteorology, which is the study of the atmosphere, and what we're going to talk about today. There's geology, which is the study of the solid Earth. There's oceanography or hydrology, which is the study of all the water. And then there is astronomy, which is the study of the universe. So we are focusing on meteorology today, which is the study of the atmosphere. So, what exactly is the atmosphere? The atmosphere is made up of layers of gases or tiny particles that surround the Earth. And once you surpass the last gas molecule surrounding Earth, um, you have traveled outside of the Earth's atmosphere, and you would now be in outer space. So this is a picture taken from a satellite, and this blue glow here that you're seeing is are the gas molecules or the atmosphere of the Earth. And the really cool thing is you can actually see like a division between the Earth's atmosphere and outer space based on the color. And so the next video that I'm going to show you is just something really cool. It's a commercial for Toshiba, but a weather balloon was attached to an armchair, and you can kind of see the change in the atmosphere as the chair is traveling upward. All right, moving on. So, what exactly is meteorology? Well, we talked about this at the beginning of the lecture, and that's the study of the atmosphere. So, a meteorologist would study any changes that are happening in the atmosphere and the conditions which affect the atmosphere. So, a question that someone studying the atmosphere would want to know is, why is the sky red? And we'll talk about that later on in this lecture. So, what exactly is weather then? Well, weather is the condition of the atmosphere at a particular time and place. So, a meteorologist is a person who studies the atmosphere and its changes. And what a meteorologist then does is they use what they know and those changes, and they can predict the weather. And so, weather is things like temperature and air movements and moisture. And those are all things that are constantly changing. And because of those changes, they bring about things like pressure increases and decreases, and things like hurricanes and tornadoes and thunderstorms. And all of those events are just things that are happening at a specific time and a place based on temperature, air movements, and moisture. So, what is in the air? The air, or the atmosphere, is made up all different types of gas particles. The gas particle that has the highest concentration is nitrogen. Nitrogen makes up 78% of the atmospheric composition. And it's kind of crazy to think about that because a huge majority of the atmosphere is made up of nitrogen, yet that's not what respirating organisms need in order to breathe and survive. What we need to breathe and survive on is oxygen, and oxygen only makes up about 21% of the gases in the Earth's atmosphere. And there are many, many other types of gases in the atmosphere, but they are found in trace amounts. So there are things like argon and carbon dioxide and water vapor and hydrogen and helium. And they're all floating around in the atmosphere, but they're just not found in very high concentrations. Another little fun fact is that it's believed that during the time of the dinosaurs, during the Carboniferous period, and all around that time, it's believed that there were higher amounts, or it's known there were higher amounts of oxygen making up the atmosphere. It was in higher compositions, and therefore that is believed to be the reason why the dinosaurs and other types of animals that were found during that time were so big, because of those higher levels of oxygen. But right now, in this day and age, the atmospheric composition is made up of roughly 21% oxygen. So moving on, what determines atmospheric layers? So what I want you to do is picture a layer cake, and that's how our atmosphere is made up. It's made up of different layers with it's made up of different cake layers with then these icing layers in between that separate each of the layers as you travel upward. So the layers in the sky are based on different temperature, and that's usually defined by altitude. So as you go up higher in the sky, or you increase your altitude, the temperature is going to change. And in many cases, it's going to get much colder, except for there's one layer where that's not the case. And there's not an exact change on a line between each layer. It's more of a gradual shift. And something else that's really important to know is as you go up each layer, there are less air molecules, and that makes the air less dense. And so as you travel up higher in altitude, because the air is less dense and there's less pressure being exerted, you would really struggle to breathe. So what I was just talking about is something called air pressure. So I'm going to show you guys a quick video clip. And this video clip is from the series Everest Beyond the Limit. And so Mount Everest is the tallest mountain in the world. And as these climbers summit the mountain or travel to try to reach the very top of the mountain, what actually happens is the atmospheric pressure decreases, and so it's harder to breathe because there is less oxygen. And so you're going to see what happens as a result of that.
Climbers on the expedition. He summited at dawn and is way ahead of the team when he suddenly stops and makes a fateful radio call.
Ross, this is Max. Can you copy me? Yeah, Max. There's a man here underneath the rock. I think he's about to die. Ross, he's unconscious. He's shivering. Is there anything we can do for this guy? Over. Can he talk at all? Negative, negative. Shivering and he's alive still, but unconscious and obviously he's not hearing what he's saying. Over. Can you get his oxygen back on? Can I stop his oxygen mask back on his face? Over. Yeah, I mean, if he's it got oxygen flowing, Max? His oxygen bottle is depleted. Listen, I'm going to try to give him some oxygen from my bottle because I have 12 bars. Yeah, Max, you can try giving him your oxygen, but, it's not going to get him down the hill. I can see where you are, so it's up to you. You can try and give him oxygen, and, you can revive him, but what are we going to do with him after that? He's a huge guy. He's almost 1,000 feet. Yeah, Max, I know it's hard, but where do we get any help? There's no more help I can see on the mountain in the immediate future to carry him down and get him down. So you can try giving him your oxygen, or you can just walk on over.
Max is
He's a good man.
And it's not going to make it.
It's easy for me to sit down here on my ass at 21,000 feet. Those guys who are up there at 28 just barely hanging on. And then they come across something like that. Yeah, Max is the hero. He's a good man.
All right, so what's happening here, and right now it's actually it's climbing season for Mount Everest. And so what's happening is that these climbers are on a summit attempt that happens every year between April and May. And as you go up higher on the mountain, the levels of oxygen decrease, not to mention the other conditions such as extreme cold, which can lead to hypothermia. But like I was saying, the oxygen levels decrease because the air pressure is much lower, and so these climbers need oxygen tanks with them as they climb up and try to make the summit. And so the hiker that was found, or the climber that was found, his oxygen was out, and Max was going to attempt to try to give him his oxygen so he would have enough to go about his normal functions and have enough oxygen just to try to get down the mountain. Air pressure is something that our bodies need, and we're used to an atmospheric pressure of 1 atm, and that allows for our lungs to expand and retract like they normally would. However, as you climb up, that pressure is going to decrease, and so your body can't function like it normally would. And the reason that happens is because as you go up higher in altitude on the mountain, there are less objects for those air molecules that are surrounding those gas molecules that are floating around the atmosphere. There are less objects for them to collide with. And air pressure comes from gas collisions. And so when you decrease the number of collisions, you are decreasing the air pressure. And as you saw in that video, there are some very, very severe effects of those pressure changes. Now what we're going to do is go through and talk about and learn about each of the layers of the Earth's atmosphere. So the first layer is the troposphere, and that is the layer that's closest to the Earth, and that's where all the weather occurs. So any weather conditions or events that are happening in the troposphere, and that contains all of the water vapor and the CO2 surrounding the Earth. So once you travel outside of the troposphere, or above it, I should say, you will not come into contact with water vapor or carbon dioxide molecules. And the temperature drops about 6.5 degrees Celsius per kilometer. So it gets very, very cold as you travel up higher and higher in the troposphere. And that is the reason why, if you've ever flown in an airplane and it's really hot on the Earth's surface, once you reach your cruising altitude and you are very, very high up, or 35,000 feet up in altitude above the Earth, you might start to see some ice forming around the plane windows, and that's because it is so cold in the troposphere at the top layers of it. And the top layer of the troposphere is called the tropopause, and that is where the temperature is constant. So if you remember, just a couple minutes ago, I was talking about picturing the layers of the atmosphere like a cake. So each layer of the atmosphere would be the spongy cake layer, and then each pause would be the icing. And once you get through the icing, or you get through the pause, then you're going to be in the next layer of the atmosphere. The next layer above the troposphere is the stratosphere, and that goes from the top of the troposphere to about 50 kilometers. And something that I forgot to mention too about planes is that the higher up you go in altitude, the less gas molecules there are. So as the planes are traveling, there are less gas molecules to create air friction with. So the planes are being slowed down less and losing less energy because of the decrease in gas molecules the higher up you go in altitude. So the stratosphere goes from the top of the troposphere upward to about 50 kilometers, like I just said, and most of the ozone is found in the stratosphere. And the temperature increases in the stratosphere due to absorption of sunlight by the ozone molecules. And something that's really cool about ozone is that it is a layer that surrounds the Earth, and we'll watch a quick video on it. But the ozone layer is the Earth's natural sunscreen. And the reason for that is the ozone layer absorbs some of the harmful UV rays that come from the sun, and those rays are what causes sunburn and skin cell mutations. So it's, like I said, it's like the Earth's natural sunblock.
In this video, we will learn about the two main layers of our atmosphere: the troposphere, full of weather and bad ozone, and above that the stratosphere, where good ozone protects us against dangerous ultraviolet light. Our atmosphere is made up of gases, mostly nitrogen and oxygen. They're held to the Earth by gravity, a sort of ocean of air. Because air is compressible, it gets less and less dense as you get further from the Earth. Let's consider the first 50 kilometers, where 99% of the atmosphere is found. Visible sunlight passes through the atmosphere and warms the ground, heating up the air at ground level. As the colder air above sinks, it pushes up the warmed air, which is less dense due to expansion. This movement, known as convection current, gives us our weather systems. The atmosphere gets colder and colder till you reach about 10 kilometers, the tropopause, where the temperature is coldest. Below this is the troposphere, containing 80% of our air, and all the weather. Above the tropopause we have the stratosphere. This is a layer of thin air which is hot on top because it's heated from above by ultraviolet radiation absorbed by the good ozone, and cold underneath, making it dynamically stable. Contrast this with the turbulent troposphere. If you have ever flown in a jet aeroplane, you may have had a bumpy ride after takeoff through the turbulent troposphere, but once you're above the clouds, above the weather, your journey is smooth. Propeller planes cannot fly this high because the air is too thin for the propeller to grip the air. So where does this good stratospheric ozone come from? Pause the video and think of the formula of ozone. Well, ozone is an allotrope of oxygen. Its molecules are made of 3 oxygen atoms bonded weakly together. It is an unstable gas which slowly decomposes back to molecular oxygen. The ozone in the stratosphere is continually being made and broken by the ultraviolet light in the ozone-oxygen cycle. To start with, UV gets absorbed in the stratosphere by molecular oxygen, which splits into 2 fast-moving atoms. These fast-moving oxygen atoms collide with air molecules around them, nitrogen and oxygen. This slows the free oxygen atoms down, enabling them to bond weakly with the molecular oxygen to form ozone. If they're moving too fast, they simply bounce off. The energy they shared with the molecules in the air heats up the upper atmosphere. The oxygen atom has now joined with an oxygen molecule to form ozone. Ozone is very effective at absorbing ultraviolet light, which causes the ozone to split back into an oxygen atom and an oxygen molecule again, keeping the upper atmosphere warm. Ozone reforms as before once the oxygen atom is moving slowly again. The ozone is spread out through the stratosphere, shown here in black. Why do you think there is so little ozone high up and low down? Remember, we need ultraviolet radiation and oxygen to make ozone. Pause and think. Well, here there is too little oxygen, and here, near the tropopause, the point of lowest temperature where the troposphere and the stratosphere join, there is no ultraviolet light available. It has all been absorbed by the ozone further out. So this is the ozone layer. If the ozone were squashed together like a solid, it would only be the thickness of a sheet of cardboard, but it is actually a gas spread out over 20 or 30 kilometers. Before our atmosphere was filled with oxygen, the UV reached the Earth's surface and prevented life from emerging onto the land. Ozone is also present in the troposphere, formed mainly by the action of sunlight on pollution from motor vehicles. Here, it helps to form photochemical smog and is a pollutant.
Right, so that was just all about the ozone layer, which is in the stratosphere layer. The next layer above the stratosphere is the mesosphere. And so that goes from the top of the stratosphere to about 80 kilometers upward. And in the mesosphere, the temperature starts to decrease again. And this is actually the coldest layer, which is about negative 90 degrees Celsius. And the mesosphere is the layer where we see meteor showers. So when meteor showers are occurring, what's actually happening is those meteors are, as they travel closer to the Earth, or as they're trying to exit the mesosphere and get closer to the Earth, they are burning up due to friction with the gas molecules surrounding the Earth, and that's why they are unable to reach the Earth's surface, because of the friction between the meteorite and the gas molecules, causing them to just break apart. So I thought this was another cool video. This is the Geminid meteor shower in Big Sur, California. The next layer is the thermosphere, and that goes from the top of the mesosphere to the exosphere, or about 550 kilometers upward in the sky. And in the thermosphere, you see an increase in heat because the nitrogen and oxygen atoms absorb solar energy, just like the ozone layer does, just like the ozone does in the stratosphere. And so the temperature can get to highs of 200 degrees Celsius. And the bottom of the thermosphere is called the ionosphere, and that's actually where the northern lights, or the aurora borealis and aurora australis, are happening. And so we'll talk about all of that in an assignment, in an Edpuzzle assignment coming up. So the ionosphere, which is in the thermosphere, that is where solar rays, or solar energy, is striking atoms that are in this layer, and it's causing the electrons to get excited, and they become atoms. And so we see that in the sky as the northern and southern lights. So like I said, we'll talk about that further in another assignment. So last is the exosphere. And the exosphere is from 550 kilometers up all the way to outer space. So the exosphere is when you are exiting the Earth's atmosphere. It is that final layer, and beyond that, you're in outer space, and you would then be studying the universe, and therefore an astronomer would be taking over. And so something else that's really cool about the exosphere is that is where the International Space Station orbits the Earth, and it does that about 350 miles above the Earth's surface, and it travels around the Earth, and it makes one full orbit roughly every 90 minutes. So the astronauts that are aboard the International Space Station see 16 sunrises a day. And the International Space Station, as it's in orbit and it's traveling at a rate of around 17,000 miles per hour. And the reason that it's able to travel so quickly without burning up is because there are no gas molecules to create friction, so there would be no heat. So it's falling at a rate of 17,000 miles per hour. And this is a really cool site that I like to visit because you are able to track the International Space Station. So you can actually see where it is in the sky at any given time. So right now, the International Space Station is traveling right over here. So it is over Asia. And if you were to come back and look at it, even within just a couple minutes, it would be in a completely different location. So this is its pathway that it's flying, or its trajectory, and we can see where it will be in 90 minutes from now. So in roughly 90 minutes, it'll be back around the Earth, right around here. So like I said, the International Space Station orbits the Earth in the Exosphere. And so that is everything for part 1 of your meteorology lecture. Thanks for listening.